12.1 Avogadros Law, the law of combining volumes. The law of combining volumes is the statement that, when measured at the same temperature and pressure, volumes of gaseous reactants and products of chemical reactions are always in simple ratios of whole numbers. For example, electrical energy can be used to decompose water into its elements. The reaction occurs at the two electrodes due to the electric current supplied by the battery. Oxygen and hydrogen gas bubbles are produced during this reaction. The balanced equation says two H2O molecules decomposes into 2 H2 gas plus 1 O2 gas. Each water molecule consists of 2 hydrogen and 1 oxygen. When water decomposes, therefore, twice the volume of hydrogen as oxygen is trapped in the collection tubes. Next, consider another example. Ammonia gas can be produced by combining nitrogen and hydrogen. The balanced equation says 1 nitrogen plus 3 hydrogen produces 2 ammonium. So the ratio is 1 to 3 to 2. The ratios are the same as the coefficients in the balanced chemical reaction. Avogadros Law. Using the kinetic molecular theory, we know that at a given temperature, all gas entities have the same average kinetic energy regardless of their size or mass. Since the temperature of the two samples is the same, the average kinetic energy of the entities in the two samples is the same. Any difference in pressure exerted on the walls of the containers can only be due to the number of entities present. We have already declared that the pressures are equal, so we therefore conclude there must be an equal number of entities in the two containers. The Italian scientist Amedeo Avogadro made similar observations. Avogadros' law is the statement that the volume of gas is directly related to the amount of gas. When the temperature and pressure of the gas remain constant, equal volumes of gas under identical conditions contain the same number of entities. We can express Avogadros' law in the equation V1 over N1 equals V2 over N2. Let's use Avogadros' law to determine volume. A balloon with a volume of 34.5 liters is filled with 3.2 moles of helium gas. To what volume will the balloon expand if another 8 grams of helium is added? Assume that pressure and temperature do not change. In order to answer this question, we need to find out how many moles 8 grams of helium is, because the number of moles affects the volume. And number of moles is mass divided by molar mass. The mass is 8 grams. And the molar mass of helium is 4.00 grams per mole. So 8 grams represents 2 moles. Step 2. Determine the final total amount of helium. The final total amount is equal to the initial amount plus the number of moles of helium added. That's 3.2 moles plus 2.0 moles. So the final amount is 5.2 moles. Next, we want to rearrange Avogadros' law to isolate the unknown variable and substitute the known values. Avogadros Law states that V1 over N1 equals V2 over N2. And we want to solve for the final volume after we add 2 additional moles of helium. In order to get V2 by itself, we're going to multiply both sides by N2. This rearranges to V2 equals V1 N2 over N1. That's 34.5 liters times 5.2 moles divided by 3.2 moles. Therefore, the balloon will expand to 56 liters when the additional helium is added. Now let's look at molar volume. Molar volume is the volume that 1 mole of a gas occupies at a specified temperature and pressure. 1 mole of any gas at STP, which is 0 degrees Celsius and 101.325 kilopascals, is 22.4 liters. 1 mole of any gas at standard ambient temperature is 24.8 liters. In this first diagram, we have 1 mole of hydrogen gas at STP, and you can see that it has a volume of 22.4 liters. 1 mole of oxygen at STP has a volume of 22.4 liters. 1 mole of argon at STP and 1 mole of Cl2. In fact, 1 mole of any gas at STP occupies 22.4 liters. Let's convert from the number of moles to the volume. A party balloon has 2.5 moles of helium gas at STP. What is the volume of the balloon? To solve this problem, we need to multiply the amount of helium gas in the balloon by the appropriate conversion factor derived from the molar mass ratio at STP. Since 1 mole of any gas at STP occupies 22.4 liters, the following conversion factors may be used. If we multiply this conversion factor by the number of moles, we will find our new volume, which is 56.0 liters at STP. Let's look at converting from mass to volume. A sample of helium at standard ambient temperature and pressure has a mass of 32 grams. What volume does this mass occupy? Let's look at how many moles 32 grams of helium is. We know that the number of moles is equal to the mass divided by the molar mass. So that's 32 grams divided by 4.00 grams per mole. We end up with 8 moles of helium. We know that at standard ambient temperature and pressure, 1 mole occupies 24.8 liters. So if we have 24.8 liters per mole times 8 moles, we end up with 198 liters at SATP. Please try the assigned practice problems in your textbook. Read over the section in your textbook and look at any LMS quizzes on this section.